In this lesson, we explore VRT, even though we have used it several times in this course, but it's time to dig a bit deeper. VRT or Vray Real-Time is an interactive rendering engine that can use both CPU and GPU. You can adjust your scene, your lights, your cameras, your materials, and see the result in real time. If I open up the render setup window, you can see VRT is available both as a production renderer, and if I change the target here, it is also available in the active shade mode. And you probably are going to use VRT in the active shade mode most of the time. So let's make sure the target is set to active shade and the render is set to VRT. And now we get a VRT tab where we can determine how VRT is going to handle the interactive rendering. The first thing you'll probably notice is we don't have as much parameters as when we were using VRADV or VREDU in the production rendering mode. For those parameters that are not available, VRT is gonna get them from the production renderer. And if you change the target to the production rendering mode and set the renderer to VRT, now in the VRT tab, you have a lot more tabs and settings that are similar to the VRADV or EDU. But in this case, if you try to render your scene in the production mode, you wouldn't have any interactivity and real-time rendering using VRT. It's just going to be a production renderer that will stop when the time limit or maximum samples per pixel has reached, and you might want to use VRT as your production renderer, for its GPU capabilities, for example. But for now, let's set the renderer in the production rendering mode to VREDU or add, change the target to active shade mode, and make sure the render is VRT. Now we can start the render and see all the adjustments that we make in the scene in real time. So let's start the render. Select the main light, which is Vray light 001, and maybe change its multiplier to 30, or use a lower temperature like 4500 for its color. Maybe we can adjust the camera view a bit. So we can see all these adjustments in real time. Now, how fast and interactive this real-time capability is depends on your hardware. For now, let's set the multiplier of the light back to 10 and its color temperature back to 6500. And let's try to change our camera view back to what it was. Let's stop the render and get back to the VRT tab. Now, the first decision you need to make is what engine type you are going to use while working with VRT, whether CPU or GPU. And there are a few things to consider when you are making this choice. First, do you have the right hardware? Do you have a video card or video cards that support OpenCL or CUDA? Have you built your machine for CPU rendering or for GPU rendering? So if you know you have a very capable CPU, you're going to be better off using the CPU engine. On the other hand, if you know there is a powerful set of video cards setting pretty in your machine, you're going to enjoy super fast GPU interactive rendering. Generally speaking, when set to CPU, you are going to get a slower render, but because the video card is not engaged in rendering, you're going to have a responding user interface. But if you decide to go on the GPU route, the render itself is going to be very fast, but you are probably going to get a sluggish user interface, which can be a real nightmare. And another important thing is the CPU engine is gonna give you a more complete set of features, while GPU rendering still has more limitations. So when the engine type is set to CPU, the CPU engine is gonna render your scene and you don't need any special GPU. We can set it to OpenCL, which in this case a GPU engine based on OpenCL is used. The engine uses graphic cards that support OpenCL and can be very fast depending on the hardware that you have. We have CUDA, which is a GPU engine based on the NVIDIA CUDA platform. This engine uses NVIDIA graphic cards that support CUDA and is the recommended engine for NVIDIA GPUs. The machine I'm using for recording this tutorial needs a serious upgrade, but it runs an NVIDIA GPU, so I can set the engine type to CUDA, and if I start the render, let's change the camera view a bit here and there. In this case, we get faster renders but more sluggish interface. So I know from my experience working with this machine that the CPU type is the best option for me. So let's set the engine type to CPU and take a look at the other options that we have. Let's run the active shade and go through its settings. First, we have the shading section. Trace depth is the maximum reflection and refraction depth of the materials in the scene. None of the materials can have a higher reflection or refraction depth than the value specified here. GI depth is the number of bounces for indirect illumination. Right now, light cache is our secondary GI engine, so this value is ignored and Vray automatically calculates the GI depths. We have auto update bitmaps. When enabled, Vray RT will try to automatically update the rendered image whenever one of the bitmaps used in the scene is changed on the disk. Use 32-bit frame buffer. When enabled, Vray RT will attempt to create a floating point 32-bit frame buffer which contains HDR information. We have lock render buffer, which is grayed out before starting the active shade, and if you enable it while running the active shade, no further changes to the scene are reflected in the RT, and the engine only refines the image, and as soon as you enable it, it becomes grayed out again, so you can't regain interactivity unless you stop the render and run the active shade again. Let's stop the render for now. We have override material, which overrides all the materials in the scene unless you exclude certain objects from being overridden by this material from this list. Let's use a simple gray material here as the override material. And if I start the render again, this material will override all the materials in the scene, and it can be very useful in the lighting phase of the project because it can really speed up the rendering. In the performance section, we have some very useful options. Array bundle size controls the number of arrays that are sent to the Vray RT render servers for processing. Larger sizes increase the speed of the render but decrease interactivity and vice versa, especially when you are working with GPU mode and you have a sluggish interface. You can decrease this value to regain some interactivity. Ray per pixel is the number of rays that are traced for each pixel during one image pass. The greater the value, the smoother the picture from the very beginning of the rendering with GI, but interactivity might be significantly diminished. And the same thing is true here, especially if you are working in the GPU mode to have a more interactive user interface. You can decrease this value, but it will result in a slower render. We have progressive RPP. When enabled, Vray RT starts rendering the image with a lower rays per pixel value and then progressively increases it. This speeds up the initial preview of the image. So if I render the scene while it is enabled, we get a very fast initial preview. But if I disable it and start the render, the initial preview is going to be slower. We have undersampling. When enabled, Vray RT starts rendering the image at a lower resolution in order to speed up the initial preview. Later, the image is rendered at its final resolution. So if I enable undersampling and start the render, you can see we get an immediate feedback, but in a lower resolution. And if I move my camera in the scene, as you can see, we get an immediate feedback, and I normally tend to enable this option while using Vray RT. We have show statistics, and if I enable it, we get some useful information on the upper right corner of the frame buffer, like Vray RT version, the number of calculated camera paths, and time elapsed since the current image started rendering. Let me disable it for now. In the next section, we have some rendering options. Max time is the maximum time for refining the image. Right now it's set to 0, so it refines the image until the noise threshold has reached. We have maximum paths per pixel, which specifies the maximum samples per pixel for refining the image. Max noise, which is the same as noise threshold in the image sampler settings, and it is a threshold that determines when to stop refining a pixel. We have in process RT engine, and when this option is enabled, the actual renderings of the image happens inside the 3ds Max process. This speeds up the initial scene translation phase, and basically it improves the interactivity of active shade rendering. When disabled, a separate Vray standalone render server is launched in DR mode to perform the actual rendering. We have distributed rendering for Vray RT. You can enable it and use the render servers button to define the machines that will be used in the process. We talked about the engine section, and when set to CPU, all the other options are grayed out as they are GPU related. So let's change the engine type to CUDA for now. We have coherent tracing, and when enabled, Vray RT will attempt to spawn secondary rays like GI reflection in similar directions in order to improve rendering speed on certain GPUs. We have GPU textures drop down. When set to resize textures for GPU, high resolution textures in the scene will be resized to a smaller resolution in order to optimize memory usage, and this parameter is only obviously available when type is set to OpenCL or CUDA, basically when GPU rendering is enabled. We have GPU texture size. When resize textures for GPU is enabled, this value specifies the resolution to which the textures will be resized. And we have the texture format that can be 816 or 32-bit. Let me set the engine back to CPU. In the geometry section, we can enable or disable certain types of geometries from showing up in the Vray RT. We have Vray proxy objects, and when enabled, the proxy objects will be rendered by Vray RT. But in the GPU mode, the proxies are not going to save their purpose of saving memory. They're going to be rendered as normal objects, and we're going to be discussing Vray proxy in our next section, definitely. And we can enable or disable the rendering of XREF scenes and containers, particle systems, displacement mapping, and motion blur. Even though when RT used as a production render, motion blur parameter here wouldn't affect anything, and the scene options will be used instead. We can also render stereoscopic effects using RT even if there isn't any very stereoscopic helper in the scene. So if I set the stereo mode to left and right and set the eye distance to something like 20 centimeters, so we can see the effects a bit better, and we know 6.5 is the standard value here, but now let's render the scene. We have three windows, a left view, a right view, and in the frame buffer we get both of the left and right eye images. And if I enable the stereo mode in the frame buffer, we can see the stereoscopic effect. Let me now disable it in the frame buffer. Now let's set the mode to anaglyph, red and cyan, and render the scene again. Now we have the left and the right eye images in the frame buffer and a separate window displaying a red cyan anaglyph of the stereo image. Let me disable the stereo mode for now. In the messages window, we can output diagnostic messages. So if I enable warn for non-physical features and unsupported features and render the scene, if there was a non-physical feature like an invisible light or an unsupported feature like hair and fur modifier, we would have seen a warning message in the frame buffer while rendering. So for example, if I select light 001 and make it invisible and start the render again, we get this green message that says there is a non-physical feature in the scene, the light is invisible. Let me stop the render and make the light visible again. And we have this message delay. When we start RT, we get some informative messages in white color in the frame buffer about the current stage of RT, and message delay is the number of seconds that information messages and warnings stay on the screen. You can set it to 0 to disable information messages completely. In the .vr scene export section, you can export your current 3ds Max scene to a .vr scene file, which is the scene description format used by the standalone version of Vray, and you can simply enable export .vr scene file, define where you want to save the file, and when you run the active shade, the scene will be exported. Or you can enable don't render, just export, and this way when you press the render button, the active shade won't start and only the scene will be exported to a .vr scene file in the specified location. And you can do the same thing in the scene. Simply if you right click in your scene, you can choose export .vr scene and export your scene in that way, and you get a bit more options, and we're going to discuss that probably in our next section. And if you change the engine to CUDA, you get a Vray RT render devices select rollout, where you can specify which video cards to use for rendering. So if you have multiple video cards on your machine, you can enable the video cards that you want to be used for RT rendering, and maybe disable another GPU so it won't be used in the RT rendering, and therefore will be free to handle the user interface, thus avoiding sluggish interface. Now if I set the engine to CPU and render the scene, if I right click in the frame buffer, we have some specific RT options. First we have real zoom, which lets us use the scroll wheel to zoom in, and it's like moving the camera in the perspective view. And double click again so we get back to our main view. We have view navigation. If enabled, we can navigate directly in the frame buffer by simply clicking and dragging. Pause lets us to pause the render and resume it whenever we want. And we can reinitialize the render using the last option. Perfect. So in this lesson, we learned about Vray RT, and I will see you in the next lesson, which is probably going to be about render elements. So see you there.